Okay, so I hope you can see my screen. Okay, so in the last class we solved up to problem number 57. So let's address problem number 58. Okay, so you can consider because it's a 2D problem. I don't know whether it's a disk or a cylinder, but whatever the case may be, you are trying to move it over this small step of height h. Okay, and mm, and uh, that disk weighs something. Okay, the disk or the cylinder weighs something. Let's say it weighs 50 kgs. Okay, so mass of the disk is 50 kgs in figure number 58. Okay, and you are trying to roll it over the edge. Okay, and you are being asked to find out how much force p is required. Okay, can you tell me how do we approach this problem? Okay. So first of all, we can think of that there is this over here. Okay, and this is your cylinder. Okay, and it is being pushed by an unknown force p, while this one is a 50 kg mass, let's say. Okay, now imagine it is being supported at two locations, a and b. Okay, so you are being asked to find out p required to roll the disk over b. That means we are not talking about actually the object rolls and accelerates or anything. Okay, we just need the minimum value of p when the rolling operation just starts. Okay, to
Sir,
start the rolling operation. Okay, so can you tell me what sort of reactions can we expect from a and b?
sir, both are normal.
No one has any idea.
Hello?
So we would start by drawing the free body diagram of the disk. Okay. So first of all, there is mg. Okay, and you can calculate how much Newton that must be. So there
Sir?
is sorry.
Yes, sir. I was trying to answer the question.
Sorry.
So I was trying to answer the question actually.
Okay. Okay. Okay.
Sir, we have to draw the free body diagram, and there will be a normal reaction from B and also from A. And the condition of the problem is that the mass will roll at B. So the condition we have to apply is the normal reaction at A becomes 0,
Hmm.
and then apply the equilibrium equations. Then we can solve it.
Okay. Yes. So you are partially correct. Okay. So the idea is, yes, in the free body diagram, there is a reaction force at A, but but at B actually. Acha. So I should mention the radius of it. Okay.
So at B it's
So
radial, right?
uh, yes, yes. So it's not just radial. Okay, I'll explain. So let's say the radius is 0.25 meter or 250 millimeter, and h is 100 mm. Okay, so let's say these are the dimensions. Okay, so at B, you are not just going to be experiencing um, a normal force. A normal force would mean that
Frictional force also.
so a normal force would mean that it passes through the center, which basically means it is going to be radial. But you see, in order for an object to roll on a given point or roll on a given line, okay, there has to be something called no slip. It cannot actually sleep on B, which basically means that at B there is sufficient friction to prevent any sliding. Okay, so the situation at B is static friction. I mean, you can imagine what would happen. Okay, let's say you are trying to go over a staircase, and if point B doesn't provide you enough frictional support, what would happen? You will simply your foot will simply skid, and you would you may get injured. But the point is, from the equilibrium point of view, or the mechanical point of view, that riding of staircase would not be possible. Okay, without the friction at that point. There is friction, and there is sufficient enough to, I mean, we are not bothering about how much is it below mu s times n. It is indeed within mu s times n. We are not bothered about that. It's just the sufficient amount, to not have any slip at B. Okay, so the point is, at B there are two reactions. Okay, and because these are two reactions, okay, which basically means I can show them like this, like a resultant, and I'm carefully choosing a broken line. Okay, the point being that I would either be showing the resultant, okay, or be showing the components. Okay, and if I show both of them in the same figure, I should not be representing them the same way. Okay, that can create confusion that there are three forces. Okay, so the R is kind of resolves into Bn and Bt. That's the idea, and R might also resolve into in the same way. It might also resolve into Bx and By. Okay, so if every time we have two arbitrary orthogonal components, we can also show them to be x and y components. Okay, I mean, so we can also show them to be unknown Bx and By. So let's do an unknown count. So By and Bx are two unknowns. Okay, I mean, you can take either Bx and By, or the Bn or Bt, or simply R and the angle that it makes with the horizontal. Okay, so all of these can be your unknowns. Okay, the resultant and its angle, or whether it's a tangent or normal component, or the global Cartesian component, whichever you choose. So essentially there are two unknowns from here. Now, of course, this one is a third unknown, but this fourth one is not an unknown. Is not an unknown. Okay, an unknown. Okay, so the point being that yes, let's say you are gradually increasing P from 0. Okay, and I know most of you understand this, but maybe some of you don't. So as you are gradually increasing P, okay, you can see essentially it is providing some moment about B, and but A is still supporting the roller, okay, or the disc. Okay, and as long as A is supporting the roller, there is not that lifting effect. Okay, we want to find out the minimum value of P at which the roller simply tries to turn over B. Okay, so we want to figure out the initiation of that, and that initiation doesn't happen as long as A is still supporting the roller. I would not be calling it supporting its weight. I mean, there are combined effect of P and the forces at B and the weight. Okay, all of which A is supporting. That means A is simply balancing all of them out. It's still an equilibrium problem. Okay, it's just that the moment A becomes 0, the reaction from A, okay, the moment it becomes 0 is what we are concerned with. Okay, I mean, since I'm calling B a frictional support, okay, you might be confused and be thinking that A might also be a frictional support. Okay, which could be true. Okay, but the point is, the lifting effect only starts when you no longer need the support of A. That means whether it's the normal or the tangential component of the force at A, that simply has become zero. Okay, so there is no unknown from A. So we are still getting an unknown count of 3, and you have 3 equations to solve them from. Okay, so now you can write your you can reduce everything into an equivalent force system to somewhere. Okay, now which point would you choose? I mean, if you go by the Bn and Bt
Sir,
representation. Yes.
sir, can you repeat the part of why we are not taking the tangential reaction force at point A?
We are taking, let's say we are taking, if you are
Because
confused, yeah, let's just take it to be I mean, let's just say there is an 80. Okay, it's just that if there is no contact, if you are about to lose contact with A, okay, then there is no normal support or frictional support or tangential support, any kind of support. Okay, the instant you are just about to roll over B, there is no support coming from A. That's the idea. Okay, so you can have your 80, but that is also zero. So that doesn't add up to your number of unknowns. Now, if you do have your Bn and Bt representation, okay, and I know some of you are smart enough to mentally solve the entire equilibrium problem by now, okay, but that's not the point. Okay. These are simple problems. These are simply examples to train you with the method. Okay, so you can possibly solve them mentally, but that's not what you should be doing. You should be following the steps. So, because just by looking at it, if I take the, you know, if I get the equivalent force system at O, okay, so Bt obviously produces a non-zero moment. Bn and P and Mg doesn't. I mean, none of Bn and Mg or P does. Okay. Now that resultant moment about O must be zero for equilibrium. Again, I'm just going ahead of myself. So Bt might eventually be equal to zero. Okay, but that is simply the solution. That's not the assumption you start with. Okay, and that's why you also show Bt in the free body diagram. I mean, instead of Bt and Bn representation, you can go ahead with Bx and By representation. Okay, then there are two unknown counts, Bx and By. Okay, but after solving the equilibrium problem, okay, because the net moment about O should be zero, okay, you'd get that this Bx and By kind of act radially, which would basically mean the component Bt itself is zero. Okay, but that's just the solution. Okay, that's I mean, using that in the free body diagram would be rendering the uh, free body diagram useless. Okay, so can you now get the equivalent force system about a convenient point? Now, I think O is a pretty convenient point, but some of you might also think B is a convenient point. Okay, so could you write the equations of equilibrium? You probably have to think of how much is this angle, given that this much is 0.25 and this much is, I mean, the radius is 0.25 and this height is 100 millimeters. So basically, if this angle right here is theta, then cos of theta is 3 by 5, okay, which basically means sine of theta is 4 by 5. So is there anyone who solved the problem?
Yes, sir. I have an answer.
Okay,
So 653.34 Newton, sir.
okay. So around 650 Newton, you are saying. Okay. So which point did you take for the equivalent force system?
Sir, B.
You chose B.
Yes, sir. Yes.
So basically there was mg multiplied by 0.2 and that would give you, I mean, sigma mz with respect to B, the net moment with respect to B
Yes,
of
sir.
all
Yes,
the
sir.
forces. So that is the, so this much, as you can see, is going to be 200 mm. Okay. So that is the counterclockwise moment, so positive, and then you should be subtracting this 0.15 times P, right? So
Yes, sir. Yes, sir. Yes, sir.
P is about 4 by 3 times mg. Which even if I think g is 10, then it is around 2000 divided by 3, which is around 667 Newton. Okay, so I believe if you put the correct value of g, you are going to get this only.
Sir, I mean 9.8.
Yeah,
In
that is fine. Okay, so I think you can solve this problem very easily by taking the equivalent force system at B. Okay. Mm,
Sir,
yes.
sir, I solved the problem, but I got one doubt that while we are writing the equilibrium condition, and
Mhm.
then we have to mention the equilibrium of the forces, right? Then
Mhm.
should I write the equation with an and at, and then put an and at equals to 0?
Uh, um,
Otherwise, will it be
I mean, yes, the
basically?
idea is correct, but if you, I mean, you must put them in the free body diagram. Okay, but then after putting them in the free body diagram, if you say mention that these quantities are zeros, okay, do that for an and at, because that is logically zero. That is the assumption that you have to make, without which you cannot solve the problem. Okay, there is a difference between mentioning an equals 0, at equals 0, and bt equals 0. Okay, but you do not mention that bt equals 0 in the free body diagram, because that is not the very assumption. Okay, ideally at the bt should not be 0. It's only by solving that you know that bt is 0, because two of the forces are passing through the center, then the third force also must pass through the center. Okay, and that basically is the so-called relation for a three force member. If there are three forces on a given rigid body, okay, and two of them intersect, I mean, let's say this is the rigid body and there are, let's say, three forces that are there, and two of them maybe they intersect outside of the geometry, but they do intersect at somewhere, let's say, let's call it O. Then the third force must also pass through that point, because otherwise there would be an unbalanced moment with respect to O. Okay, and what we have learned that I can get the equivalent force system about any point in the universe. Okay, the resultant force and moment must be 0. Okay, now if the two forces intersect, the extended lines of intersecting, let's say, intersect at O, maybe even outside of the geometry. Okay, and third force doesn't pass through that. Okay, so these two forces do not produce any moment. The third force would be producing some moment about that force, and therefore it would not be in equilibrium. Of course, you can also realize that this is not the signs should be. I mean, the direction of this force must be in opposite. Okay, so in order for this rigid body to be in equilibrium, the third force must also pass through the point of intersection of the lines of action of the other two. That's quite a big statement, but I hope you understand what it means. Yes, I got a little diverted from the topic that you mentioned. Yes, so that comes from the solution. Okay, so that bt is 0 comes from the solution. You don't have to mention that. Okay, right after you drew the free body diagram, you don't have to mention that. I mean, you can actually put an equals 0 and at equals 0 in the free body diagram. That is absolutely fine. You can logically explain why you think that that should be 0, because it is about to roll over B, so it is going to lose contact with A. It is about to lose contact with A, so the moment that happens is when AN and AT equals 0. Okay, just mention that. Okay, and then thereafter you don't have to show them in the calculation, not even in equivalent force system, not even in the equations of equilibrium, nowhere. Okay, but when it comes to BT, okay, you'll have to do the entire exercise, go to solution, and it's only by solution that you know that BT would be 0. Okay, so you'll have to do that solution, and then you can say that BT equals 0. Okay, so later on when we move to solving structures, okay, when we will be addressing the equilibrium of structures which would involve more than one rigid bodies, before going there we would learn about three force members. Okay, and once I can identify an object to be a three force member, then I know all the three forces when the object is in equilibrium, okay, must pass through a single point, and if two of them are already passing through one, then the third must also pass through that. Okay, so you either draw the free body diagram completely and solve that BT equals 0, or you can use that three force member analogy, which we have not learned so far. Okay, so once we have learned that, we can use that. Okay, so I think you can pretty much solve this problem. It's not a complicated problem. Neither is the next one. So look at this. So this rod has to be in equilibrium. Okay, and you are actually being asked to find out. So the bar weighs 150 kg. Okay, and it's a uniform bar. Okay, so you know where the center of mass should be, and that's where the weight is acting. Okay, and it is receiving some support from A and B. Okay, and some tensile, some upward force coming from the cable which is applying a tensile load. So the cable is under tension, and it is under tension because the bar is pulling it, and it is also in turn pulling the bar in the upward direction. Okay. Now in this problem, okay, it is not mentioned whether or not the surfaces at A and B are smooth. Okay. So what do you do in this case? Do you consider the frictional forces? Please remember, free body
Yes, sir.
diagram.
Yes, sir.
You do consider. You are saying you do consider.
Yes, sir. Yes, sir.
Okay. So there is tension from the cable. Okay, and let's just put the dimension. So this much is 5 meter. Sorry. So this much is 5 meters, and the other part is 10 meters. So which basically means in another 2.5 meters. Okay, so this. Okay, sorry. This one is 12. So 5 is this and 10 is this. Okay, understood. So that basically means this is not 5 meters. This is 4 meters. This one is 5 meters. And this one is 10 meters. This entire portion. But then you can identify the. No, it would probably be a little left. This is the center of mass or center of gravity, you want to call it. So that would be in another 2 meters, right? So how do I know in another 2 meters? Because the entire bar spans of 12 meters. So 6 and 6. Okay. Now this point is called A and this point is called B. Okay. See, dimensions must be there properly in the free body diagram. Okay. Now, the simple reason I would not consider the frictional forces. Okay. And if nothing is mentioned, I'll mention that I'm assuming the walls to be smooth. Okay, if the no comment has been made regarding the smoothness or the roughness of the surfaces, I'll simply assume them to be smooth, because with only 3 equations I can solve for 3 unknowns, and these are my 3 unknowns. Okay, some problems may be a little ambiguous. Okay, but there I'll have to make some approximation which is justified. You see, even if there are frictional support, okay, they have to be through static friction, right? And static coefficients of friction are much smaller compared to 1. Okay, so typically friction forces are smaller than the normal forces. And in a situation where I can only accommodate 3 unknowns, I would rather neglect the frictional support. Okay, and unless it is specifically mentioned the surfaces are rough, okay, I can assume them to be pretty smooth and more or less uh, the normal forces represent the resultant force. See, one more thing I'd like to mention. Let's say if sine theta, or actually sine phi, where phi is the angle of friction. Okay, so let's say there is normal force, and then there is friction force. Okay, and together they make the resultant force. Okay, so angle with n should be the friction angle phi. So r sine phi is f, and r cos phi is n. Okay, and if sine phi is, let's say, 0.2, cos phi would be square root of, which is approximately, you can check, this is what the answer is going to be. Okay, the point is, the for a low coefficient of friction, okay, or the normal force and the resultant force are essentially of the same magnitude. Okay, so using all that understanding, I would say that I would simply neglect the frictional support because I don't have enough equations. Okay, so now for this geometry, okay, let's call this point as C. Okay, try to get the free body diagram. Now, no, this is the free body diagram. Try to get the equivalent force system, and you can actually get the equivalent force system about any point. Let's say some point where you can neglect a couple of forces. The point might also lie outside of the geometry. So you can get the equivalent force system about O. That is also fine. And if you are bothered about heights, it's quite obvious that if this is so this much is 6, right? 6. So this much is 4.5, and this is another 4.5. This much is 3. So find out the reaction forces at A and also the tension in the cable.
Sir,
Yes.
sir, it's coming 326.67 Newton.
For what?
So for AX and BX.
No. What is whose value are you calculating? Whose
So
value
what
are
is
you,
the mass? Can you repeat once?
sorry, what is the
Mass of the rod is the
oh
rod.
yeah, it's 150 kg.
So the normal reaction force at A and B is coming 326.6.
Okay, so the normal reactions are same, right? AX and BX.
Yes,
Yes,
sir.
sir. Yes, sir.
And what are their values?
326.67 Newton.
Okay. And tension must be equal to mg, right?
Yes, sir.
Okay. So around 1500.
Yes, sir. 1470.
Okay. So I think we did although very few 2D problems, okay, but the understanding can be extended and you can try more problems. Okay, so that is independent of what assignment I'm giving you. The assignment has only this set of problems. I just wanted to check whether you are doing them properly. Okay, uh, but practice more problems from the textbook, more problems from the problem sheet that has been given to you. The problem sheet essentially has questions from the textbooks only, but I would suggest whatever textbook that you are following, whether it is Medium Craig or by Hibbler, okay, from that practice enough problems, okay, enough that when you can try any problem in that chapter, or you can solve any problem in that chapter, as long as you do not have the confidence to do that. Try as many problems as you require. So number one,
Sir,
and both of this, let me finish. Both of these chapters are important. The equivalent force system, the chapter on equivalent force system is important, and so is the equilibrium chapter. Okay. So yes.
sir, there was one request, sir. Up till this 27th, from 24th, 27th, we have our English Viva Voca exam.
Okay. Okay.
So, can you please extend the submission date of this assignment at least till next Wednesday?
So next Wednesday.
Means it's 23rd, 30th.
And I understand, but you see, these are the problems that are actually solved in the class, right? I just you need to make a fair copy of that. Why do I need that? I want to check that you are understanding the steps and you are following the steps correctly. Okay. I hope I understand that you have exams going on, but I'm not. The only thing that would be requiring is you to make the proper steps. Okay, like a lab report. Okay, make it or an exam paper. Okay, just do it like a fair copy, not like a rough copy that you do. Okay, so what I would do is so maybe you can submit them by 28th. Okay, so instead of 27th, okay, you can submit by the Monday night. Okay,
Okay,
so that
sir.
I can check them by Tuesday, and we can have a discussion on Wednesday as well. So next week I'm targeting to cover your structures, and in structures we will be only solving frames. Okay, so 1 hour on Monday. Actually, we can also have our doubt clearing session. Okay, and after that we will move to structures, and Wednesday also we'll probably be continuing that. Okay, since I mentioned 3/4 member, okay, let's try this. Let's clear up the 2/4 and 3/4 members. Okay, ideally I should be leaving them for structures, but since we mentioned them, so we can actually so so that will actually give a will prepare for your structure problems. Okay, so imagine there is this rigid body right here. Okay, and it has two locations, A and B. Okay. Or let's say this body right here. And let's say there are tiny holes over there to join them through some pin joint to other components. Okay, and let's say these two locations are A and B, and the rigid body is only receiving forces at these two locations. Okay, that means it is not, all the forces that are being applied to the body are at only these two locations. Okay, same over here. Okay, so the purpose of the exercise that we are about to do is to pre-solve some of the rigid body problems. Okay, some of the rigid body equilibrium problems. Okay, to make the process of solving solving multi-body equilibrium when we are working with structures, there we have multiple rigid bodies forming a structure, right? So there, in order to study the equilibrium, we'll have to study the equilibrium of all the rigid bodies, right? And if there are 5 of them, 5 is too much, let's say 3 or 4 of them, then you have in 2D 12 9 to 12 equations to solve for. Okay, but if you can identify one of them to be a two force member, what is a two force member? A body, a rigid body on which the forces are acting at only 2 locations. Okay, which means this object is not on the vertical plane, and even if it is on the vertical plane, okay, the object itself is weightless. These are the assumptions, because if you are to consider the weight, that might act through a different location, right? Okay. So there would be a third location through which another force passes. So that is not allowed. We are only allowed to consider the forces acting at 2 locations. So those objects we would call them as two force members. Now, the two forces A and B could be arbitrary. But when they are in equilibrium, or if they are in equilibrium, these two forces are not arbitrary. Okay, but when you are identifying a two force member in an equilibrium problem, okay, the forces at A and B are not not arbitrary. Okay, first of all, for this object to be in equilibrium, sum of all the forces must be 0, right? Sorry, sum of all the forces must be 0, but there are 2, which basically means if A and if B are equal and opposite. Okay, so this goes to 0 for equilibrium. So if A is minus if B. Okay, so two forces are equal and opposite. Okay, now let's draw them as equal and opposite. For the first diagram, I probably did that already. So it is minus FB. So there I need to draw, sorry. Yes. So this FA is minus FB for equilibrium. Now next, so now look at these two diagrams. Okay, FA equals minus FB. So there are two forces equal in magnitude, opposite in direction, acting on the same rigid body, but not along the same line. So what does these two forces form? Or what do we call these two forces? Equal in magnitude, opposite in direction, but non-collinear and acting on the same. That's a couple. And a couple would have a non-zero couple moment. And that couple moment is about any arbitrary point. Okay. But if there is a couple moment, okay, how can the object be in equilibrium? So the point is that this FA and FB, not only are they equal in magnitude, opposite in direction, but they also act along the line joining AB. It has to be. Otherwise, they are going to be non-collinear. So this is your FA and this is your FB. And that is irrespective of the shape of the object. Okay, so you'll have to identify the line joining AB, and the forces simply are along that line. So for this rigid body right here, using all the 3 equations of equilibrium, okay, we have identified the direction, direction of the 2 forces that are there at B and A, okay, and the fact that the 2 forces are equal in magnitude and opposite in direction. So the only thing that is left with is the magnitude of FB. Okay, so you only have to determine this unknown, only one unknown. Okay, by that I mean By that I mean the number of unknowns. Okay, let's say for a 3-digit body structure would have been how many? 9 equations of equilibrium, 9 unknowns, right? But with the understanding, okay, or the pre-solved uh, understanding of the two force member, if one of the members is a two force member, then for that member I have only one unknown. Okay, so that way the number of unknowns reduces from 9 to 7. If I'm working with 2 rigid bodies, number of unknowns reduces from 6 to 4. Okay, that's how advantageous this exercise is. Okay, but when it comes to a 3 force member, the only idea that we have, okay, if so whatever I said earlier, if two forces are intersecting or their extended lines of action are intersecting at certain point, maybe even outside of the geometry, then the third force must also pass through the same location. Okay, that is the only way it is going to give you equilibrium. And actually, this representation is wrong. I mean, you can already figure this out. But you don't have to bother about that while drawing the free body diagram. It's only after solving that you can also get the signs, okay, and then you know which one is facing which way. Okay, so the third force passes through the point of intersection of the other two. If it were not passing through that point, it would be producing an unbalanced moment about this point, and the other two would not, because of which the object could not be in equilibrium. Okay, now see all of these conditions on 2 force and 3 force members, that the forces be collinear, equal and opposite, or the forces be concurrent. Okay, so all of these conditions are applicable only when the object is in equilibrium. Okay, if it is accelerating, if it is moving, you cannot make that assumption. Okay, so but this representation is seldom helpful, and the point is in all intents and purposes you will be solving a 3 force member like a regular rigid body. I mean, in this problem, let's say for the third force, okay, third force you already know the direction. Okay, so it's the magnitude of the third force, maybe a reaction force. Okay, so let's say if you're looking for a reaction force which has two components, okay, you know the ratio of the two components. Let's say F3 is your reaction, and F1 and F2 are external forces. So F3 is what you are trying to determine. Okay, so in this case uh, you have determined the ratio of the two components, okay, but not the magnitude of F3. Okay, that you can only get after solving the problem. Okay, so this if the 2 force member reduces number of unknowns by 2, a 3 force member reduces number of unknowns by 1. So if you are dealing with 9, then it would become 8, 6 it would become 5. Okay, so yes, so we'll apply all of this in the next class, where we'll be solving structures. Okay, so now let's move on to 3D problems. Okay. So before going into 3D problems, let's look at some of the supports that are there. So the first one is like, so we are showing only a portion of a rigid body. Okay. So imagine some end of the rigid body is like this broken shaft over here, and this very end is basically spherical, and it has been placed on a surface which just might provide some friction. Okay. So imagine drawing the free body diagram. So first of all, I'll get rid of the ground. Okay. And let's say if the surface is frictionless, okay, so you can imagine a single support reaction which would be RZ. But if the surface provides friction, then you might also expect Rx and Ry. Okay. Now in the next example, there is a channel.
Sir,
Okay. Yes.
so can you explain the picture once again?
Okay, so this is one end of the rigid body, which is simply put on the ground, on a surface. Okay. And no other constraint. So of course it cannot penetrate the ground, which is that normal to the ground. There is of course one reaction. This is the obvious one. But then you also come to know that the surface is rough. Then you would be getting reactions in Ry and Rz. Okay. That means the surface doesn't let the object slide in X or Y. But the surface being spherical in nature, okay, there is no restriction over rotation. I hope you can understand that. That means with respect to its spherical end, the rigid body itself can perform rotation about any axis. And that's why you see the sphere contacts the surface at a point, right? And you cannot provide a moment support at a point. Okay. For example,
So the ball and socket joint.
it's not a ball and socket joint. It's not a ball and socket joint. For example, if I mention the surface is smooth, these are not there. It's not even preventing the sliding. But you see the sphere contacts the plane at a point. Okay. And you can never, provide a moment through a point. Okay. For example, if you let your pen touch the plane of paper, okay, it cannot prevent rotation of the pen because the ball tip of the pen is actually having a point contact with the surface of the paper. Okay. A point contact cannot prevent rotations. I hope you understand that you need more than a single point contact to prevent rotation. Okay. For example, if I place my pen, okay, lie it down on the plane of paper. Okay. Now there is a line contact with the paper. Okay. And you cannot rotate the plane, not at least, in the downward direction, perpendicular to that line. So when you have a line contact, that is able to prevent rotation. But when you have a point contact, there is no, when you touch the plane of paper with the ball tip of your pen, okay, so there is no restriction on the even with all the friction that the surface of paper can offer, the ball can rotate about any axis by any arbitrary amount. So there is no restriction on moment. So there is no moment restriction on rotation. So there is no moment support, moment reaction. Whereas if you place it on its side, if you place the pen on its side on the plane of paper, okay, along that line of contact, imagine you are trying to you know rotate in a way that the displacements on the displacements on the pen are perpendicular to that that line of contact of the pen with the paper. Okay, you cannot do that, right? Because the pen cannot penetrate the surface of the paper. Okay, whereas, for example, if I take my pen and place it like this on the paper, okay, so now this is the line of contact, and I cannot simply rotate about, let's say, this axis right here, which would require the pen to move like this. I cannot do that, okay, when I have a line contact. But place that pen on its tip on the plane of paper, okay, now the pen can rotate about any axis by any amount. So so obviously it doesn't provide any moment support, but if it is smooth, if the surface is smooth, it also doesn't provide support against sliding. Okay, Achha. Let's move on to the next diagram. Okay, so you have this thing moving on a channel. Okay, and although it is not mentioned, you'll have to assume that the wheel can never leave the channel. Okay, now, obviously, to the rigid body, there is a support going in the z direction, RZ. But you see, this rigid body can now move along x-axis, okay, freely. So there would be no reaction force along x-axis. Okay, it cannot move vertically downward. Therefore, there is reaction force coming from the z direction. Also, because it cannot leave the channel, okay, you can imagine the two ends of the channel is actually slightly protruded vertically. So there is some reaction force in the y direction as well, not preventing the object leave the channel. Simply it cannot move along y axis. Okay, and now when it comes to moment, okay, can the object rotate about y-axis? This is the y-axis. Yes, it is free to rotate about y-axis. So no reaction moment about y-axis. Can the object rotate about z-axis? Do you think the object can rotate about z-axis? Because in order to do so, the wheel have to be misaligned with the channel. So do you think the object can rotate about z-axis?
No, sir.
Even I think it cannot rotate. So I would be experiencing a resultant moment, a reaction moment coming in the z direction. Okay. And x-axis, it is free to slide, but can it rotate about x-axis? If the channel is such that the wheel cannot leave the channel, wheel cannot be misaligned with the channel. Okay, those are not shown. Okay, but those are implied. Okay, with the the tiny shape that has been provided to the channel. So if it cannot leave the channel, do you think it can rotate about x-axis? If it cannot, then there would be a moment support which is preventing it, a moment reaction which is preventing it. Now the third one is pretty simple. That's a ball and socket joint. Okay. So what does the ball and socket joint do? The ball and socket joint essentially prevents translation in any direction. That is, this green part prevents this orange part from moving in X or Y or Z, but it cannot prevent the rotation about any of the axes. So the rigid body, the orange part, can actually rotate about X or Y or Z freely. Okay. So in the ball and socket joint, okay, what sort of reaction we would get? Would we get any of the reaction moments? Because the ball and socket joint do not prevent any rotation, we would not be getting any reaction moment. But since it also doesn't let the object to move in either X, Y, or Z, so you'd be getting all the three reaction forces. Okay.
Sir, the first example with friction, is it the
Yes.
same?
Yes.
Not technically, is it the same as
Yes.
this?
The first example with friction is essentially a ball and socket joint. As we discussed earlier also, that friction kind of acts like a pin joint when it comes to 2D problems, right? Static friction in equilibrium. So it's the same analogy. Okay. The next example is a fixed joint. So you can imagine a portion of the body is inserted into the ground. Okay. And actually none of the degrees of freedom. Okay. So I am not sure whether I mentioned the word degrees of freedom. Okay. A rigid body in 3D has 6 degrees of freedom. That means translation in 3 perpendicular directions and rotations about 3 perpendicular axes. Okay. In 2D, it has 3 degrees of freedom. So that is ux, uy, and theta z. Okay. So what do I mean by degrees of freedom? Degrees of freedom essentially here, okay, in different context, it could mean a different thing. Okay, but in mechanics, a degree of freedom would essentially represent the kind of motion that an object can have. Okay, so a rigid body, you can imagine in 2D, it can move independently in x direction, and whether or not it moves a certain amount ux in x direction, okay, independent of that, it can move an amount of uy in y direction if it is completely free. Okay, then irrespective of whether it's let's say the center of mass moves certain distance in x or y or not, okay, it can independently rotate about its center of mass by an amount of theta z. Okay, this is the center of mass moves by ux. You see, when I'm talking about rotation, okay, I'll have to talk about translation of a single point. So irrespective of whether or not it is moving certain distance in x and y, it can independently rotate a rigid body. So in 2D, if it is free, so that accounts for 3 degrees of freedom in 2D. Okay. And it can do 6 of those in 3D. There is translation about 3 different axes, translation in 3 different directions, and rotations about 3 different axes. So that accounts for 6 degrees of freedom. Okay, and every time a degree of freedom constrained, you have one reaction and I am not mentioning whether it's a force or a moment. That depends on whether it's a translatory degree of freedom or a rotational degree of freedom. You have one reaction in that degree of freedom, in the direction of that degree of freedom. So if you are trying to prevent the motion of a given point in y, let's say by putting a roller support, then you are providing a reaction force, okay, in y direction. The reaction force might as well be 0, okay, but that is there. So if you are trying to prevent the motion in a given direction, you are doing so by providing a reaction force in the direction of the motion, okay. As I mentioned, there are 6 degrees of freedom of a rigid body in 3D. Now, when you completely fix a rigid body, let's say if you take this end of the rigid body and simply bury that in the ground, okay, and or simply weld it with the ground, okay. So now you are left with this portion of the rigid body, okay, which can have no relative motion with the ground. And in a situation like that, it cannot move in x. So let me draw the axis. So it cannot move in x, it cannot move in y, or it cannot move in z, or it cannot perform rotation about any of the axes. So therefore, it will be receiving reaction forces in all the 3 directions, because through these reaction forces is that that support, that fixed joint, okay, is trying to prevent any kind of motion of the rigid body. So this reaction force are there to prevent the motion, okay? And then you have mx, my, and mz, okay. So that is the 4th one, and then the last one is look at the last one, okay, and please note how the diameter of the shaft changes from left to right, okay. Now can you tell me what sort of reactions would be there, or what type of motion would be prevented for the rigid body, which is the orange one, of course. The green one is actually the part of the ground, okay. It is it is fixed to the ground. So can this rigid body translate in x?
No, sir.
Okay, so there is Rx.
Sir.
Yes.
Sir, it will have 5 reactions except the moment about y.
Okay, let's just derive that, okay. So since it cannot move in x, okay, so there is Rx. Can it move in y? Try to answer that.
Yes, in one direction it can.
So only
Yeah.
in one direction.
Sir, it
Yes.
can yes, a negative y direction.
Yes.
It can move in negative y direction. That's what the diagram tells you. But by this representation, what is meant that the type of load that would be acting on the body would rather have a tendency to move in the positive one. That's why that other end is being made thicker. Okay, so in a way, this tries to tell you that the translation in y direction is also prevented. So it would be receiving Ry. Okay. Now what about Rz? Will there be a reaction force in z direction? Or
Yes, sir.
is the okay. Because the motion in z is also prevented. Acha. Next, talk about rotations. Now it is obvious that it can rotate about y-axis, so there would not be any reaction moment in y direction. Okay. Can it rotate about x-axis?
No, sir.
No, sir. No, sir.
No. And by the same analogy, can it rotate about z-axis?
No, sir.
No, sir.
And that is the correct answer. So there would be 2 reaction moments, mx and mz. But I'm just going to show you another thing, and that is, so this is your rigid body, right? This is the thicker portion. Okay, and this is your support, and this is a thinner portion coming out. And this kind of fixed with the ground. Okay. Now you are correct in thinking that it can rotate about y, and it cannot rotate about x or z. Okay, but you'll have to understand one thing. Of course, there is certain amount of clearance between the smaller portion of the diameter. And imagine if this thickness of the support is substantial, okay, then you are correct in thinking that there would be no rotation about the x-axis or z-axis, because again the cylinder has line contact with its support, or itself has this cylindrical surface contact with its support. Okay, this is the contact area, and you are correct in thinking that the rotation about x or z would be impossible. Whereas if I make this thickness very small, so much so, this is no longer a cylindrical surface contact. It's a line contact. What do you think happens if it is a line contact? If it is so tiny that it is almost negligible in thickness, and essentially the rigid body forms a line contact with the support here, that is not going to prevent the rotation about x or z. So if it is really thin, you can imagine it can do at least partially, it can perform certain rotation about x or z. Okay, to understand this, take a piece of paper. Okay, make a circular hole with your pen and insert your pen or pencil inside this, and check whether you can rotate it slightly about, let's say, 2 of the axis of
Sir,
yes.
sir, but the paper is flexible. If
No,
we take a
no.
Yes, sir. Yes,
Don't,
sir. Then the
yes, I understand the paper is flexible, but don't let the paper be distorted. Okay, just make the hole slightly wider, slightly bigger. I mean, there should be some clearance between the pencil and the hole. Okay, now I'm not actually asking you to do that. Mentally do this exercise. Do you think you can do a little, not a full rotation, but little rotation about these 2 axes that are part of the plane of the paper? Do you think you can little bit tilt the pencil?
Sir, we can, but like in my mind, it is happening because of either there is a give, like there is a space between, like it's not completely in contact, or because the paper is bending, it's flexible. If those 2 are eliminated, I don't see how it can rotate.
Okay. So the point actually is, in a physical situation, there is of course some clearance. Okay. In an actual support like this, there is obviously some clearance. Okay, number 1, and number 2 is I mean, when you do consider clearance, then this T doesn't actually have to tend to 0. If it is sufficiently small, that would be good enough. Okay, so in that situation, you can actually perform a little bit of tilting of this shaft. Okay, in either of these 2 axes, this one or this one, and that little bit of tilting, okay, although it's not completely free to have any arbitrary amount of rotation, that little bit of tilting is not actually as good as fixing those degrees of freedom, and therefore in that situation you can think of those moments are not acting.
sir.
Not at least in that configuration. Okay, once it is slightly tilted and then comes in contact with its support, then probably there is a moment. but not before that.
Sir, then I can say if the cylindrical, the diameter of the cylindrical hole is larger than the diameter of the shaft, then only
Yeah,
it will.
it is larger, right? That's how you inserted it. Okay.
Okay, sir. Okay, sir.
So there is some clearance. But the fact is, when that support, the point here is when it is really thin, that support is really thin, is that you can consider uh, mm, a possibility of having somewhat tilting about x and z axis.
Sir,
Yes.
sir, I don't understand. Like, what does it have to do with the diameter of the hole? Like, if there is clearance in any sized hole, wouldn't it rotate anyway?
Yes. I mean, if you are saying that a pen shaft like this or pencil like this, and then a hole like this, that's not the physical situation, right?
No, no, sir.
Typically,
I was saying like it is like the difference is the same. Like it's a large diameter object or shaft inserted in a large diameter hole, but there is clearance. It can
yes,
still rotate, right?
yes, it can rotate.
So, sir,
It can
what
rotate.
is the significance of the thin?
Oh, then thickness, right? Yeah. So then you'll have to take a section and imagine.
Sir,
Yeah. Let me try to answer this question. Then we'll address the next one. Okay. Okay. Now, obviously, I'm showing the clearance in a quite the exaggerated way. That much clearance would probably not be there. But do you see the picture that if I make this thinner, the constraint is lower, and if I make this wider, the constraint on rotation would be higher? I just took a section along a XY plane of the joint right there. Does this picture make a little sense to you? That making this really thin wouldn't probably have that much constraint. I mean, of course, the clearance is not going to be this high, right? Not this much higher.
So that means how much we can rotate the shaft, that will depend upon only the thickness.
Yes. Here also we are talking about, let's say, mm, uh, let's say if it is a very small clearance, there is a clearance but very small clearance. Okay. Now think in this way, if it is a quite wide support, okay, so practically you would be not be seeing any amount of rotation. But if it is a really thin support, possibly it doesn't restrict rotation as much as it would have has it been much wider. That's the idea.
sir, but if we have to make something, if we have to lose contact with any of the point, then sir, it will become it will become a very variable one. Means then we have to remove one reaction along any one of the axes. Means like if there is a gravity, then it would tend to rest on the lower part, so there will be an RZ. But and for the timing, there is
No. I have one objection to that thinking. I don't care whether there is gravity, whether this everything is in the vertical plane. If what you are considering z-axis is the vertical direction, I don't care. Okay. The way I propose reaction forces and moments is just by looking at a support, standalone. My criteria is what motion does it constrain effectively, and then the reaction in the same direction.
okay,
I don't
sir.
have nothing.
Sir, but if it has to conduct a rotation in the xy plane, means along the z axis, then it must have some clearance in the in the x direction means, if I consider the
Yes,
x,
in the x direction,
then
yes.
so then Rx means there is no contact with that means what means the holes, there will be no contact between the shaft and the holes for that x direction. Then the Rx will
Yeah. Let me tell you this. Okay, and let us put an end to this discussion. You see, there are two faces. Okay. I mean, the way I would be imagining, okay, that it is either in contact with this face or this face, at least, if not with both of them. Okay. It is so the motion in X is always supported. So every time you try to, this is not how we should be thinking. But let's say if I try to load it in X direction, it would not be moving in X direction because at least this face or this face, okay, would be in contact with the, would rather eventually come in contact with the edges. Okay, this edges, and that is good enough for supporting in a given direction. Okay.
okay sir, okay sir.
Okay. Okay. So let's start solving this problem. So in the first problem, problem number 61, okay, you have at A ball and socket joint. Okay, and the two unknowns are T1 and
Sir.
T2. Sorry.
Sir, sorry to
Yes.
disturb, sir. In the last problem,
Yes.
while we will draw the FPD, then there will be some reaction force along X and Z direction, and there will be some moment along X and Z direction.
Mm-hmm.
But sir, the shaft can travel along the minus y direction, right? Then we will have to show some reaction force along the positive y direction.
No. Again, that is wrong thinking. The reaction force is there because the object cannot move in a given direction. Okay. The next point is the purpose of design where only the negative side of the shaft has been made thicker, not the positive side. That also has a reason. Okay, that design also has a reason, and the reason being that the designer anticipated that with all the other kind of loads, the shaft would kind of try to move in positive y. Okay, and that had to be prevented by making it wider in the left hand side. The diagram could be confusing, but that was in the mind of the designer. Okay, so in a way, the representation, or rather what it means by that diagram, is the translation in y direction is prevented, and the reaction forces is y is due to the fact that the translation in y direction is prevented, not because the translation in y direction or negative y direction is possible. Does that answer your question?
Yes, sir. Yes, sir. I got it.
Okay, so the first problem, okay, you have okay, and A is a ball and socket joint. Okay, it seems that we would need Monday to even cover 3D equilibrium problems. So
This was in the sheet, right? All of these.
these are in the sheets. Okay. Okay. So yeah. So what we will do is we will not actually solve these problems. We will simply discuss about them, and they would be your assignments. Okay. I know that 3D problems can be a little scary, but we will address the way they should be. Achha. So in this problem, and it has been the bar at its midway is being pulled in the negative y direction by a force of 4 kilonewton. Okay, and that 4 kilonewton force, and you can consider the bar to be weightless. Okay, you don't have to consider the weight of the bar. This bar must be supported through that ball and socket joint at A. Okay, and you know by now that what a ball and socket joint means. It means that there are 3 reaction forces and no moments, and 2 cables T1 and T2. Okay, so how many unknowns do you have in this problem? You are actually supposed to determine the tensions in the
So
cable.
the unknowns will be T1, T2, and Rx and Ry. And
Okay. I don't know how you are, thinking process is working. The thinking process should work in this way. What type of support is there? Okay, I would not be mentally calculating what reactions would turn out to be positive or negative. I should not be thinking in that way. Okay, it's a ball and socket joint, so 3 reaction forces. Okay, that's the idea, because it is preventing 3 translations and no rotations. If the ball and socket joint was the only thing that is to be there, okay, in absence of all the cables and all the forces, the ball and socket joint could only prevent translations in 3 directions. Okay, so the reaction coming from A are Rx, Ry, and Rz. So 3 reactions from A, rather 3 unknowns from A. Then there are 2 unknowns T1 and T2. Okay, so you have to solve for 5 unknowns from what? 6 equations of equilibrium. So you can get the equivalent force system about one of the points, and it seems because Rx, Ry, and Rz are passing through A, maybe A is a convenient point for getting the equivalent force system. So you can get your equivalent force system about point A, no problem in that. Okay, let T1 and T2 be unknowns. Let Rx, Ry, and Rz be unknown. Okay, get the equivalent force system about A. The resultant force and the resultant moment. Okay, or the equivalent force and the equivalent moment. Let that be at A. Okay, and both of them must be equal to 0 for the equilibrium. That's the idea. That's what we have been doing for 2D problems, all the 2D problems. Okay, so it's getting an equivalent force system. You have done that for 3D problems, no issue. Okay, and the idea is just that moment will be having 3 components and the forces will also be 3 components. So unlike 2 and 1 in 2D. Okay. So you'll have the reaction force and the reaction moment at A. Okay, the resultant force and the resultant moment at A, considering all the reactions at A. So the resultant force also includes the reaction forces from A, right? All the forces. So, I mean, you could also try to get the equivalent force system about B. So there you should be also considering the reaction forces coming from A. Okay, so you'd be trying to replace the reaction forces from A to B. And for that, you need to do that moment correction and whatever we have discussed for equivalent force system. So get the equivalent force system about any point, okay, and equate them to 0. Okay, and then once that is equated to 0, you can solve for your unknowns. But my question is, you have 5 unknowns to solve from, and you have 6 equations of equilibrium. And how is that justified? You see, if I were to get the equivalent force system about A, I hope you understand the question. We have 5 unknowns to solve for. Okay, ideally you should be having 6 unknowns. Okay, or in other words, how can only 2 tensions keep the object in equilibrium? It's because actually with only 2 cables, okay, in this problem, you can support a 4 kilonewton force that is being applied. Okay, but if I were to apply a moment about axis AB, with these 2 cables, you would not be able to support. I'll simply explain. You see, if I'm trying to get the equivalent force system, so I'm solving a different problem here. I'm trying to see if I have the post. Okay, and instead of 4 kilonewton force, I have simply applied an external moment M. And let's say this is the force T2 coming from the cable. This is the x-axis. This much is 5 meter. This much is 10 meters. And this is the y-axis. This is the z-axis. So this is 4. This is 2. And this is another 2. There is another cable going from B to D. And sorry, I believe this is B to C. And this one is A. Okay. Now I'm drawing the free body diagram. So I will be drawing the reaction forces, that is RZ, RY should be in this direction, RY and RX. And while doing that, I'll not be thinking which of the reaction forces should actually be 0 and all. Okay. Because that's not my job while drawing the free body diagram. So let's say, and let me tell you, this is absolutely not how you should draw the free body diagram. Free body diagram should be neat and clean. Everything, the axis, the direction, the dimension should be clearly comprehensible. Okay, it should be as good as the drawing that you are being provided. Okay, and but of course not that drawing, because this one is shown with all its support. I am not showing the cable. I'm showing the tension coming from the cable. I'm not showing the ball and socket joint. I'm not showing the ground. I'm showing the reaction forces coming from it. So okay, so T1 and T2 are there. So if I were to apply this moment about z-axis, can it support this? Think about this. If I am trying to get equivalent force system about A. Okay. Now I'm just drawing roughly. This is not how you are supposed to draw. You get a resultant force over here. Okay. And then let's say this is the resultant moment about A. Now this quantity, let's say it should be 0 for equilibrium. This is a condition of equilibrium. But can this be equal to 0? You see, the moment coming from T2 and T1, they have no component along z-axis. You see, it is because I can calculate the moment of T1 and T2 by taking the position vector of B with respect to A. And that position vector is 10K, which means that the moment of T2 and T1 about A has no Z component. Okay, they only have X and Y components. But then I'm applying externally this moment about z-axis. So let's say that this is the moment about moment due to T1 and T2, which is along XY plane. And this is the moment that I'm externally applying. Okay, so there is no way this can balance this one. Okay, the resultant moment would not be 0 and the object would not be in equilibrium. Okay, so all I'm trying to say here, using these two cables, it's not sufficient support. It can support the object, it can keep the object in equilibrium when you are actually applying a 4 kilonewton force along y-axis. Okay, again, please understand, when you are applying a 4 kilonewton force, okay, at a location whose position vector can be given by 5K, so that 4 kilonewton force is also not creating a moment about A, which has a Z component. That's why T1 and T2 keep the object in equilibrium in presence of this 4 kilonewton force, which it could not be in if I were to apply external moment about z-axis. Okay, number one. Number two is, while writing the equations of equilibrium, one of the equations of equilibrium, rather one of the moment equations, okay, would have a 0 equals 0 form. Okay, because you see the moment due to T1 and T2 would be 0. Okay, and therefore, or for that matter, the 4 kilonewton force would also be equal to 0. Now you are supposed to, when you get the equivalent force system, okay, in an equilibrium problem, when you get the equivalent force system, you are supposed to equate the resultant moment and also the resultant force, okay, equal to 0, which basically means sigma fx equals 0, sigma fy equals 0, sigma fz equals 0. Okay, the moment equation becomes mx equals 0, sigma mx equals 0, sigma my equals 0, and sigma mz equals 0. Now, the expression for sigma mz, that is in terms of T1, T2, and 4 kilonewton force, that itself is 0. So the third equation is redundant, useless, 0 by 0 form, 0 equals 0 form. Okay. The other equations, that is these 3 plus these 2, are actually the useful equations, and they actually would lead you to the solution of the 5 unknowns that are there in this problem, which are the reaction forces at A and the values of T1 and T2. Okay. So try to solve this problem on your own. The idea is simple: get the equivalent force system about A. Okay, and so first draw the free body diagram, then get the equivalent force system about A, and simply equate the resultant force and the resultant moment to 0, because that's how you get the equilibrium. It's simple. Okay. So try to do that. Okay. Then the next problem is equilibrium of this particle. So this time it's not an equilibrium of rigid bodies. This time involves equilibrium of particles. And for particles, this is what you do. You have the first equation and not the second equation. So take all the forces in there. You see, you have been given these 3 cables, okay, whose unit vectors you can figure out from the position vectors of the points A, B, C, and D. Okay, so you can figure out the unit directions or unit vectors. You do not know the magnitude of the tensions in those cables. Okay, but once you write the 3 equations of equilibrium of the particle, that is A, okay, then from the 3 equations you can solve for these 3 unknowns, which are the tensions in the cables. Okay, so already it is 32 student count. Okay, so half of you have already left. Achha. But I hope you would be watching the videos. Okay, so let's just do one thing. Try to solve the first 2 problems. Okay, so by Monday just solve the first 2 problems, and then we continue from the third problem, from problem number 63 onwards on Monday. Okay,
So what is the answer of figure number 61?
I don't have the answer to anyone. Okay, I believe because I have solved it probably 15 times, I believe it is 2 root 5 and 2 root 6, like 4.9 and 4.5 or something.
So
Yes,
T1
sir.
is 4.9. It was in the sheet.
The T1 is 2 root 6 and T2 is 2 root 5.
Yeah, I recall that from memory, but I don't have the answers. Okay, actually you can also try to solve the problem number 63. In problem number 63, just read carefully what it does. The post is supported at O, which prevents translation in all directions, okay, and also prevents rotation about Z. So the only 2 motions that it doesn't prevent is rotation about X and Y. Okay, so the idea is you get all the reactions, that is Rx, Ry, Rz, and Ox, Y, and Oz, and the reaction moments, let's say Mz, but you do not get any reaction moment in X and Y. That's the idea. Okay. So after that, you will have to solve all the variables. So basically, the tensions in the 2 cables and the 4 unknowns that are there at O. So total 6 unknowns you will have to figure out. Okay. So yes. So let me finish. So your assignment would be to finish up to problem number 63. The rest you will solve in the Monday's class.
Oh, sir, I was actually asking that only. The assignment we have to submit on 27th, by 27th. How many problems do we have to do?
Up to problem number 63.
Okay, okay.
Okay. And I believe problem number 64 also you can do. 66. I mean 66, not 63. Just try to figure out what sort of support you can get from this prism. So on Monday, we will be solving these two problems, 64 and 65. Okay. So rest you can, rest should be your assignment. So up to problem number 63 and then 66.